Long before steam powered mines or factories, people already noticed a simple fact: heated water pushed back. In the 1st century, a Greek engineer named Hero of Alexandria built a small device that proved it. Steam rushed through tubes and made a hollow sphere spin like a toy driven by invisible force. It showed motion could come from steam. But it solved no urgent problem. It stayed a clever demonstration, not a working machine. That gap mattered. Knowing something could move and making it useful were very different tasks. Early societies had strong sources of power already: human labor, animals, wind, and water wheels. Steam, by comparison, looked expensive and hard to control. It demanded sealed vessels, careful metalwork, and steady heat, and those were not easy to guarantee. So inventors treated steam as a surprise of nature. It entertained, it puzzled, and then it sat on the shelf. Centuries later, in early modern Europe, experimenters returned to the same idea. They heated boilers, watched pressure rise, and imagined devices that could lift or push. But again, the leap to industry never arrived. Materials leaked, joints failed, and results stayed small and unreliable. Most designs could not run day after day, doing heavy work for a profit. Steam power existed as a possibility. The world still lacked the engine that made it necessary. By the late 1600s, mining faced a simple crushing limit. As shafts went deeper, water rushed in faster and work stopped. Horses and hand pumps helped, but only up to a point. In 1698, an English inventor named Thomas Savery stepped in with a bold claim. He patented a machine that used steam to lift water out of mines. It sounded like an answer industry had waited for. Savery's pump did not try to turn wheels or run factory machines. It aimed at one job: moving water. Steam pressure pushed water upward, and when the steam cooled, it created a vacuum that pulled more water in, ready for the next push. The cycle relied on heating and cooling again and again. Savery packaged that idea as a product, not a laboratory trick. He tried to sell steam power as useful work. That step mattered because it changed the question from whether steam could move to whether steam could pay. Savery's design faced hard limits in real mines, especially as depth increased and pressure demands rose. Yet the patent marked a shift in ambition. Steam power entered the marketplace as a proposed solution to a costly industrial bottleneck. Even when the pump disappointed, it proved the need was real and the race had started. By 1712, the need underground grew more urgent than any promise on paper. Mines went deeper and water came in faster. A Devon ironmonger named Thomas Newcomen stepped into that pressure with a new kind of machine. It did not try to push water up with steam directly. Instead, it used steam to drive motion first, and that motion worked a pump. That shift made the difference between an idea and a working engine. Newcomen's design became known as an atmospheric engine because ordinary air did much of the heavy lifting. Steam filled a cylinder, then cold water cooled it. The steam collapsed and a vacuum formed. The outside air pressure forced a piston down. That up and down stroke pulled on a beam, and the beam worked a pump rod deep in the mine. It sounded simple, but it finally matched the brutal daily demands of mining. The result mattered immediately. Mines that had stalled at flooded levels reached deeper seams, especially in coal. And coal did more than heat homes. It fed the furnaces that made iron, and it fueled the engines that drained more mines in a tightening loop. Newcomen engines spread because they solved a clear problem reliably where the fuel was already nearby. Steam power stopped being a novelty and became a tool of Britain's coal economy. By the middle of the 1700s, Newcomen engines no longer looked like rare experiments. They sat beside mine shafts across Britain, working day after day, keeping deep coal seams from flooding. But each new installation brought the same trade-off. The engine solved the water problem, then immediately created a fuel problem. It burned coal in huge amounts. And now there were enough engines running that nobody could pretend it was a small cost. At first, owners accepted that appetite because the alternative was simple: lose the mine. When a pit had coal right beside it, the waste felt almost invisible. But as engines appeared in places where fuel had to be hauled in, the bill stopped being tolerable. The math turned harsh. Much of the heat went up the chimney or was thrown away inside the machine itself. Every stroke that pumped water also advertised inefficiency, loud and constant. So the pressure shifted. The question was no longer whether steam power worked, because it clearly did. The question became whether it could be made to work without eating profits alive. Mine managers, investors, and engineers started looking for savings in a way they had not before. Small adjustments could not keep up with rising fuel costs and growing demand for power. What the moment required was not more tinkering, it required a step change. In the 1760s, a young instrument maker named James Watt received a task that sounded routine: repair a small working model of a Newcomen engine. But as he tested it, the numbers refused to make sense. The engine did its job, yet it burned through heat for no good reason. Each stroke asked steam to do work and then threw that hard-won heat away. Watt tracked the loss to one repeating mistake. The cylinder needed to stay hot so steam could push properly. But the Newcomen design cooled it down on purpose to make the steam collapse and pull the piston back, so every cycle heated the metal, then chilled it, then reheated it again. Fuel paid for that swing. The engine spent its strength fighting its own design. Watt's solution sounded almost too simple: separate the jobs. The cylinder could stay hot all the time, while the steam could be condensed somewhere else. He imagined an extra chamber kept cold, connected by a pipe where steam could be collapsed without chilling the main cylinder. This separate condenser changed the balance. The same engine power now demanded far less fuel, and efficiency stopped being a dream. By 1775, Watt's improved engine no longer faced a technical problem as much as a practical one: getting it built, sold, and trusted. That year, he partnered with Matthew Boulton, a businessman who understood production and scale. The deal changed the stakes. Watt brought the design and the careful thinking. Boulton brought organization, money, and the drive to turn an invention into a product. Instead of a few engines built slowly and close to home, the partnership pushed toward regular manufacturing and a wider market. They aimed at mine owners first, because mines already paid heavily for pumping and fuel. Watt's efficiency now became a clear financial argument. Less coal burned meant lower running costs. That single advantage did what clever mechanics alone could not. It made customers willing to switch. As more engines were built and installed, the new design stopped being a one-off improvement and started behaving like a system that could spread. Each successful engine helped sell the next one. The partnership created a pipeline from idea to installation, and that pipeline reached beyond a few local mines. Steam power began to look less like a specialized solution and more like a dependable business tool. In the 1780s, James Watt pushed his engine past the job it had first dominated: pumping. The missing piece was motion that could do more than rise and fall like a simple pump rod. His answer was rotary motion, turning the engine's back and forth movement into a steady vrachenia that could drive a shaft. That sounded technical, but the result felt simple. Steam power stopped being a special tool for mines. It started acting like a general source of power. With that turning shaft, the engine could connect directly to factory machines. It could spin looms, power rollers, and keep equipment moving at a controlled pace. Watt's other refinements helped make this reliable: smoother delivery of power, better control of speed, and less waste. The engine no longer had to sit beside a single pumping job. It could sit at the center of a whole building and feed motion outward, belt by belt, machine by machine. That change broke an old constraint. For generations, factories had depended on water wheels, which meant building where fast-running water existed, not where business wanted to be. Steam rearranged the map. Now a factory could rise closer to workers who needed jobs, closer to ports that received raw materials, and closer to markets that bought finished goods. Water still mattered, but it no longer ruled. In the 1780s, power became portable enough to follow people and trade, not rivers. By the early 1800s, a different kind of steam engine pushed into view. Earlier engines stayed huge and cautious because they ran at low pressure, but some builders gambled on higher pressure steam packed into smaller cylinders. That change sounded technical, yet the result felt simple. The engine no longer had to be a permanent building. It could be a machine that moved. In Britain, an engineer named Richard Trevithick built engines that ran on high-pressure steam and delivered strong power from compact parts. It made boilers and pistons work harder, and it made the whole system lighter. That unlocked a new idea. Steam could drive wheels. Trevithick's experiments pointed toward locomotion, not just pumping or turning factory shafts. Across the Atlantic, Oliver Evans pursued the same shift in a practical American way. He pushed for high-pressure engines that could be built, transported, and put to work wherever power was needed. Instead of bringing materials to a fixed engine, the engine went to the job. Portable steam promised to cut time, labor, and distance. Steam power became mobile muscle. By the 1820s, steam stopped being a clever machine and became a system that reorganized daily life. Railways spread from one line to networks, and schedules started to matter as much as distance. A journey that once took days by road took hours on rails. Coal, iron, and finished goods moved in bulk, reliably, and year-round. Time compressed, markets expanded, towns that sat on a rail junction grew fast. At sea, steamships changed the rules again. Wind still mattered, but it no longer decided everything. Steamers followed routes that merchants could plan around, and ports became linked by regular service instead of hope and weather. Rivers opened inland regions to heavier trade, and ocean crossings became more predictable. That predictability pulled more raw materials into industrial centres and pushed manufactured products outward, tying distant economies into the same rhythm. Inside factories, steam power scaled up production in a way older sources could not match. Machines ran longer, faster, and in larger numbers, and employers demanded steady labour to keep them fed with coal and materials. Prices fell on many goods, while competition intensified and smaller workshops struggled to keep up. Industrialisation spread beyond Britain because rails, ships and machinery travelled together. The result reshaped work, migration and global trade. By the time the modern age arrived, the classic steam engine no longer sat at the centre of daily life. Cars, trucks and airplanes depended on internal combustion and gas turbines. Factories relied on electric motors that started instantly and fit almost anywhere. Steam still worked, but it asked for boilers, water, warm-up time and constant supervision. In most places, it simply lost the convenience race. A different kind of steam power took over instead. Electricity demanded huge, steady power, and steam delivered it in a new form. Rather than pushing a piston back and forth, steam now rushed through a turbine, spinning blades in one smooth motion. That rotation turned a generator, and the generator made the current that ran lights, machines, and cities. The fuel source changed from plant to plant, coal, oil, gas, nuclear heat, but the middle step often stayed the same. Heat boiled water, steam did the turning. So steam did not disappear. It retreated from streets and shop floors and settled behind the switch. The old engine that once pulled water from mines left a long shadow, even after newer machines took its visible jobs. In power stations, the principle remained brutally simple. Make heat, make steam, spin metal, make electricity. What looked like an ending became a transformation. Steam power ended up less familiar, but more widespread than ever.